Yeah.
All right. While they're going around, I want to do this problem, then we'll take questions on the inductive transient problems, and the similarities by now are obvious. But I want to make sure everybody can see this. This is the quiz problem. And it simply has a 20-volt battery source. It has a switch that closes at t equals 0. It has 2K, 3K, 500 ohms, has a capacitor here. And this is VC, and this is I know. And that's what they want. So for this problem, again, I think this was literally the first problem I put on the board related to this. It was literally that problem. I changed the values and that was it. So when you take a look at this, first thing you find for t less than 0, VC for t less than 0 is, you got to inspect this. Well, the thing isn't even connected, the voltage source, so it's got to be 0 just by inspection. Everybody see that, class? It's 0. Has to be. Next, after the switch closes, now we go for t greater than 0. Find the voltage as t goes to infinity. So for this one, I'll just draw this up here. I didn't look at everybody's paper. I looked at a few. And I mean, a lot of people, they got this. They know what they're doing pretty much. But there's enough people that, from what I've been told too, that they didn't understand it. I'm just going to encourage you all, make sure you spend time on this stuff and really know it. Because remember what I'm saying. All this stuff builds. It's not disjoint. If you don't understand the first set with circuit analysis, you'll never understand this. And if you don't understand this, then stuff to come is going to be very hard. So try to make sure you play the game and you stay, you can't cram for this. You got to stay up with everything. I'm just warning you and trying to encourage you as best I can. So now we do for t greater than 0 what the circuit looks like. I'll put it for you here. Now you've got this voltage source. And then you have 2K, 3K, 500 ohms. And I want the voltage as t goes to infinity, so what I'll do is actually say this. I want this voltage. I'm going to remove the capacitor like I did before. Because I know at infinity, nothing's changing with time. So I want that voltage. You all follow me in this class? Make sure you do. How many see this right here? You good with it? All right. Now, if you see that, you all see that what I've got here is a series circuit, don't I? Of 3 resistors. I'm going to do this. You don't have to. I'm going to combine this 2 and 3 and just make it 5K. All right? Everybody see that? Because it's series. So I just make one value here. And make it 5,000 ohms or 5K. And now you can see really I've got 2 resistors in series. Y'all follow me, class? So the voltage across here where the capacitor was at t equal infinity, because it's an open circuit, right? The capacitor looks like an open circuit at t equal infinity. That voltage is just the voltage across the 500 ohm. And it's simply going to be 20 times 500 over 500 plus 5K or 5,000. And that's really 20 over 11 volts. It doesn't matter if you put it in that if you put it like that or put it whatever the fractional form is. Y'all agree with that, class? Slightly less than 2. All right. Now, the next thing you need, right? You got the voltage at T equals 0, voltage at T equal infinity. Now you need R Thevenin, correct? This is the part I'm going to make sure you see. R Thevenin is the resistance, Thevenin equivalent resistance, that would appear for T greater than 0 across that capacitor if it was the load. Do you follow me? I'm going to use this big drawing here to make sure everybody sees this. So I'm going to go ahead and shut this switch. And then I'm going to remove the capacitor, because this is what I really want. I want R Thevenin here, right? Get rid of that for now. Now, what do we do with sources? We turn them off, right? So voltage sources become shorts, not opens, right? Short circuits. So this becomes a short circuit. And then you can see what? The 2K and 3K are in series. They're 5K. Some of you see this, I mean, just automatically. You don't need me to say this, but. So I'll just replace those with 5K. Or 5,000 ohms, if you will. And now, you all see that they're in parallel? So the Thevenin value would be this in parallel with this. And I don't care how you do it. You can put 1 over 5,000 plus 1 over 500. And that really is what? That's 10 over 5,000 plus 1 over 5,000, or simply 5,000 over 11 ohms, isn't it, class? However you want to do it. And if you want to multiply R1 times R2 over R1 plus R2, it's fine with me too. Y'all with me on this, class? All right? It's as obvious as it looks. I mean, there's nothing tricky about this. Now that we have that, right, R Thevenin, next thing we need is tau. And tau for this is going to be R Thevenin times C. So it's 5,000 over 11, or times C, and C is 100, correct? 100 microfarads, or 10 to the minus 4. Right. And that, it depends how you want to do this. So 0.5 over 11 is tau. And you can write it down in the decimal form. Everybody follow me on this, class? Can hear you?
What does it say in the parentheses?
That's 10 to the minus 4. It's 100 microfarads. Micro is 100 times 10 to the minus 6 is really what? 10 to the second times 10 to the minus 6 is 10 to the minus 4. Do y'all follow me?
Sure.
That's all I meant to do by that. And so now when I've got that, now I put together my equation. And I know over here, I said that VC of t is equal to some K1 e to the minus t over tau plus K2, correct? That's what it's always going to be. K2 is the voltage as t equal infinity. And that voltage, I have right there 20 over 11 volts. So then I can say that's K1 e to the minus t over tau plus 20 over 11 volts is VC of t. And I know at t equals 0 at 0, correct, class? So the only thing I do is 0 would be equal to K1 plus 20 over 11, or K1 is equal to minus 20 over 11. Y'all follow me? And then you can, I mean, it's just straight, right? I mean, nothing tricky about this. It's as obvious as it seems, and don't make it more complicated. It's not meant to be complicated. When I come down to here, now I put down VC of t. And you can put it any way you want. You can write it as 20 over 11, right? 1 minus e to the minus t over tau, and I'm just going to leave it as tau. And that's the voltage across the capacitor. Y'all follow me? And again, do it methodically, just like I did. You'll never mess these up if you do it. And do your circuit analysis right. Now, after that, the next thing we're going to do is find the current through that 500 ohm resistor. I erased that circuit, but you all see how that 500 ohm resistor was in parallel with the capacitor? How many see that class? I know I erased the drawing. With me? You all see it in the back? All right, so the current was straightforward. I naught of t would just be VC of t divided by 500, and that's it. Well, you can put in, I mean, if you put in the numbers, you get 20 over 11 divided by 500 times that expression, 1 minus even minus t over tau. Now, one thing that he apparently saw was people just put single numbers for VC. They put like 12 or 5 or something. And you know, these are transient problems. They have to be a function of time. I mean, a single number tells the grader that you really don't understand the problem. And you have to make sure you understand these well, because this stuff comes at you and there's more coming. And you really have to have it down. All right? All right, next, inductor problems. So, when we're dealing with inductors, they're similar to capacitors. They're energy storage devices, but what's the big deal? With inductors, we need to know the current, not the voltage, right? And they look like shorts when nothing changes with time. Unlike a capacitor, it looks like an open circuit. So, here we go. All right. Do you have a problem for me? I gave you several, didn't I? All right. Any problems at all? I always take it from the audience, usually because you guys, those are the ones you've been thinking about and discussed. Go ahead. Did you have them? Or not?
No, sir.
Yes?
Could you do 336?
336, sure. Yeah, this is a good problem. And by the way, you can see how these problems really, they require you to have a fairly good understanding of circuit analysis. If you don't, then you jeopardize everything. So you have to know the first part to know this part. So for 336, you've got 36 volts. Two ohms. Okay, this switch is closed at t equals 0, it opens. Then you have 6 ohms. You have an inductor here of 2 henries. Then you have 4 ohms. And 8 ohms. And they want this current. And that's a red flag. You don't care about that current. Not yet anyway. The thing with an inductor, please hear me. You're only after the current through the inductor for t greater than 0. You could care less about whatever else they ask. You get that after you get that current. Y'all hear me on this, class? That's it. You're just worried about this current right here. That's the only current that you're looking for. And the way you realize it, the IL of t, it will be some K1, an arbitrary constant, e to the minus t over tau, plus K2. Here, K2 is the current at t goes to infinity. All right. And the way you do these problems is just the same way as you did for the capacitor, only instead of voltage, now it's current. So the first thing you find is IL for t less than 0. I want to tell you one other thing. you notice how for this problem, the direction of current wasn't defined through that inductor. Do y'all follow me on that? It wasn't defined. Define one. You can have it going that way or that way, but you have to define one. My general rule of thumb, if I'm ever given a choice, I take current going from the top to the bottom, from the left to the right. You follow me? So I define that as my current I'm going to solve for. Now, if I solve for the one going up, those constants would be negative, so don't worry. The equation works, it would just have different values. Do you follow me on this, class? We're going to find the current here. So first thing is, I got to find the current for t less than 0. What does an inductor look like for t less than 0, class? What is it? Yeah, but what does it look like whenever nothing's changing with time? A short circuit. Do you hear me? It looks like a piece of wire. That's what it is, just a wound piece of wire. So if we look at this thing, here's my circuit. I got 36 volts. Then I got 2 ohms. Remember, that switch is closed. Then I've got 6 ohms here, right? And then I have where the inductor was. Now I'm going to replace that inductor with a straight wire. I want this current. And then I have this. Does everybody see this 4 and 8 can be combined to 12? Do y'all see that? In the back there, can you all see this? They're in series, aren't they? So just make them a single value of 12. I want this current right there. Right? How do I get it? And you can do it any way you want. I mean, you could do it Thevenin, you could do it. How would you get it, guys? No?
Combine the 6 and the 12.
Go ahead, keep going.
Combine the 6 and the 12 because they're parallel.
So she's saying 6 and 12 are in parallel. That's 4 ohms. Do you all agree with that? Everybody? 4 ohms.
And this 2 is in series.
So that's 6 ohms total, right? Do y'all hear what she's saying? She's got those 2 in parallel. 4 and 2 is 6, right? And that's in series with what?
36.
All right, so what she noted was that there's 36 ohms of resistance to that source. Do y'all hear? I mean, there's 6 ohms of resistance, right, to this 36 volt source. Or isn't the current flowing here equal to 36 by 6 or 6 amps? How many see that? Shut this off. Are you with me, class? So if I have 6 amps here, first, how many see it's 6 amps flowing here out of that 36 volt? You got it? All right. You see the 6 and 12 are in parallel? That's 4, right? And the 4 ohm would be in series with 2, correct? That's 6 ohms, right? So if 6 ohms is put across the 36 volt source, you would get 6 amps, wouldn't you? 36 by 6 is 6 amps, right? Okay. Everybody? So 6 amps is flowing, continue here. How do I get the current here? You're right.
6, oh.
Y'all see these 2 are in parallel, right? Isn't current division appropriate here, class? Sure. If I want the current through that 6 ohms, I would say I would take that 6 amps, the I through the 6 ohms, would be the total current flowing into both, 6 amps times the opposite resistance, 12 over 12 plus 6 or 18, right? Or this would be 6 times 2/3 or 4 amps. Take a look at this. Do you agree with that? How many see this right here? Huh? It's straightforward current division, isn't it, class? In the back? All right, now what? I got that. I got the current for T. That is the current for T less than 0. So let me put them over here. Now, what's the next step? I mean, this doesn't have to be in particular order, but I like to get the current in the inductor as t goes to infinity, right? What's the current in the inductor when t goes to infinity and why? Now what happens for t greater than 0? At 0, what happens to that switch, class? It opens, right? So it's not there anymore. This would be the state of the circuit for t greater than 0. Do y'all agree with that? Now, isn't that totally disconnected from this side, right? So what I'm going to do to make it absolutely clear is just erase it. There's no way that stuff can influence the other side, because current can't flow. Y'all follow me? Now, if you look at that, what is the value of the current as t going to infinity and why? Why though? You're right.
Because there's no source.
Nothing can sustain it, right? It's going to die down to be 0. There's not a battery or current source or anything in there, right? And remember, if current's flowing, there's resistors, power is dissipated, it will go to 0. That means IL for t goes to infinity is 0. Now, y'all follow me on this? Now the next thing is what? I've got to find R Thevenin, right? Remember, we have to find R Thevenin. So what I'm going to do, this is for the circuit for t greater, just erase that inductor. Do y'all follow me? Because that way you'll see this. If I erase the inductor, here's where I want R Thevenin. Y'all see that the Thevenin equivalent resistance is just a series combination of all those? How many can y'all see this, class? And you guys in the back can see this, right? So that's going to be what? 12 and 6 is 18 ohms, right? Y'all get? All right. So that means R Thevenin is 18 ohms. Now tau for an inductor circuit is not L times R. You remember what it is? This is tau for an LR circuit. That's L over R Thevenin, isn't it? Remember me doing that last time? The bigger L is, the larger that time constant is. Or the slower the circuit decays, is another word to say it. Another way of saying it. So L for that one, was it 2? I forgot. So it was 2 over 18 ohms, or simply 1/9 is tau. With me? Finally, once I have this, now I set up the equation and solve it, right? I mean, this is everything I need. I've got current t less than 0, current t equal infinity. There's my equation, right there. Now what's really nice about this is what? When this thing is 0, when the current at t, as t goes to infinity is 0, I know K2 is 0, don't I? And if K2 is 0, K1 is just the current for t less than 0. Isn't it, class? How many see that right there? So now I can say, for this equation, IL of t, based on that reasoning, this becomes 4 e to the minus t over tau. Well, tau is 1/9, so t over tau would be 9t. And it's plus 0, so that's IL for t greater than 0, or equal to 0. Follow me? Now, what's the value of this current based on my IL? Remember, my IL was what? I've got IL now. I have IL of t. I put that in there. So what is that value of I that they're solving for right there? How many see it's just the negative of mine, right? Sure. So now I can say that the I of t they want is just minus IL of t, and that's minus 4 e to the minus 9t for t greater than or equal to 0. And that's really it in a nutshell. Got it? Yes, sir?
Will you explain why it's just the negative version?
Well, you can see that this current would be circulating in the counterclockwise direction. They want the current in the clockwise, right? So it would be just negative of that, wouldn't it? If you've got 5 amps going this way, it's like minus 5 amps that way, isn't it?
And so, and all those resistors are in series, so it's the same current flowing through all of
It has to be, yes. Yeah, and if there were parallel combinations, then we'd do current division. You with me on that? Now I got a question for you.
I got a question for previous that, on the I 6 ohms, on the current division, why you put 18? And there's.
Well, no, 6 amps was flowing into the pair of 6 and 12, right? When we looked at this, we had basically this. 6 amps, and then we had 6 and 12 ohms, right?
Oh.
And what we wanted is the current through there, right?
Yeah.
So you take the 6, multiply it by the opposite 12 over the sum to get that, okay? Everybody good with that, class? All right. But now let me get to my question. So on a quiz, and this is just basic, if you don't understand the basics, this is a no-brainer. If I asked for the voltage across this 8 ohm, plus to minus, how would you get it? It's as obvious as it looks. We got the current, don't we? We take that and multiply it by 8, right? Check that box. Don't wonder about it, be sure of it. Y'all follow me on that?
It
I
would
mean-
still be the negative.
What, no, I'm saying you've got this current already. We know it's the negative, okay? So if I have that current, I just take that and multiply by the resistance. There's nothing to ponder. It's that straightforward. And that's what I'm trying to really get across, because when people are wondering, oh, should I multiply it or not by the resistance? These tell me that you really don't understand. This should be second nature, honestly. You've had it in physics. Now you're having it here. You probably had it in another class, but this really is straightforward stuff. There's nothing, I promise you, this is not deep stuff. The differential equations, where they're statistical, like IEs like statistical stuff. All right, if you did it that way, that would be a pain. But we're talking about something that's just deterministic. There are no values that are changing in time with resistance and stuff. We're not looking for a family of curves to represent the outputs. Thank God. All right. Another one. That was a good one. Try to remember this too. Voltage is like electrical pressure. Current is like the water flowing. It's the amount of water flowing. Always try to keep these things in mind. All right, you got another one for me? For anybody? Guys? No? In the back? Okay. You don't have another one? No? All right, I do. I got several for you. This one's a little trickier. I have time. Okay, breaking up. I only have 130. All right.
That's correct.
Hmm?
That's correct.
Okay. This is 340. So here, these are just ohms. But here's the problem. And again, what I may see, I hope I don't, is somebody write an equation for V naught. Don't. All right, what did I tell you? The first thing you do is find the current through the inductor. Correct, class? Always, that's your focus. So this one is not, that doesn't define a direction. I always go from top to bottom, from left to right. So I call that IL of T. Y'all follow me? I have to supply that information. Got me on this, class? Now once I do that, I know that equation will be of the form K1 e to the minus t over tau plus K2. I know it's going to be of that form. What is K2 again, class?
It's the voltages.
Not voltage.
Current as it approaches infinity, time approaches infinity.
Current as time goes to infinity. Remember that, all right? Remember that. I like to get, I want to make sure everybody's got that in their mind. Now, the first step I usually do is the current through the inductor for t less than 0. Correct? That's the step I always take. It's either the voltage across the capacitor for t less than 0 or the current through the inductor for t less than 0. So what does this circuit look like for t less than 0? Now here's what I like to do too. Just, I'll tell you straight up. I see a circuit like this. I try to simplify anything I can. Who sees something I can simplify? Anybody? Go ahead.
Those 2 3s on the left side are in series, and then that
All right, hold on. How many see these 2 3 ohms are in series? Y'all see it? I'm gonna replace that by 6, all right? Y'all see this? So, don't keep going yet. So this is 6. Everybody see that, guys? All right, no, not you, somebody else. What's the next, what else can I do? Anyone? Go ahead.
How those are in parallel.
Yeah, now they're in parallel, right? Replace those by 2, right? You could take 6 times 3 over 6 plus 3, right? 18 over 9 is 2 ohms. Everybody see what I'm doing here? How many agree with that, by the way? I want to make sure. Can you all see it? So this is going to be 2 ohms. Remember, we're not getting into anything on that side. We're just simplifying over here. Make life easy. Life is already hard enough, but I can make it harder. Simplify things. And as engineers, there's one piece of advice I can give you. Anytime you can simplify something, do so. It'll save time and it helps you understand. Now I get down to that point. Remember, I want to get this for t less than 0. What does the inductor look like for t less than 0?
Short circuit.
Everybody hear that? Short circuit. It's a wire, just a wire. So here I have 2 ohms. That's what a short circuit means. Replace it with 0 ohms or a wire. Then I've got this. I'm going to leave this switch out because that thing's open. So don't even put it in. Then I come over here. Here's my inductor. And that's the current I'm after. And then there's 2 ohms. All right, now take a look at this. Can you all see if I want that current? These 2 ohms are in series, correct? Everybody see that? Far back, guys, can you see? So that's 4 ohms. The thing that's driving current clockwise is 6 volts. Do you agree? So 6 volts over 4 ohms would be the current. Do you all agree with that? Therefore, the current there would be 6 volts over 4 ohms, or 3/2 of an amp. Okay? Follow the thought process, it's important. Now, I want to look at the current as t goes to infinity. I always like getting that one next. You don't have to get this one next, but I like it. And again, now we're going to take a look at the state of the circuit when the switch closes. Do y'all hear me, everyone? All right, when the switch closes, this becomes a short. And I'm going to ask you something to make sure you see this. When that closes, y'all see that this is the same electrical potential as that point. Y'all see that? Effectively, this part of the circuit is removed entirely. Do y'all see that? This can have no influence on that side because this is the same voltage as this forevermore. There's no way you can get a voltage difference to change things on that side. So just remove it. Because that's a short circuit is effectively the same electrical point. Y'all follow me? Now, what don't you understand? When that switch closed, you understand it becomes a straight wire? What does a straight wire really mean? It means electrically, this point is identical to this point. There is no difference. So it doesn't matter if you put a battery out here with a resistor, right? It doesn't matter because the current flowing through here can't develop a voltage. There's nothing it can do to affect the other circuit. That's the idea. If you put, it's called a short across something like this, just 0 ohms, it isolates that part of the circuit from that completely. Now,
Because there's nothing like resistor like that. Voltage flow, so the voltage will automatically just flow on that circuit.
it's current that flows, not voltage.
Oh, yeah, the current.
The current can flow, but it's flowing in a zero conductance path, so no voltage can be developed. All right?
And then if you were to put a resistor there, then.
That's different.
Yeah.
Then all bets are off. All right? But for the problem stated, the switch makes that point electrically that point, and it just completely omits, causes that first part of the circuit to be gone, effectively. You all with me? Now, when I look at this, what is the current going to be at infinity and why? Think about it just for a second, and then give me a reason. What is it?
0.
Why?
There's no source.
Nothing out there to keep it from not being 0, right? It's going to decay to 0. I want to show you. These problems are that simple, I promise you. But people make them harder because they want it must be harder than that. It's not. It's that simple. Trust me on this one. I mean, the MEs and A's, I have an appreciation, thank you, for some of the stuff that you go through. I know you have very complicated systems. I don't know about that, but I know about you guys. And you always are looking for, oh, I must overlook something. Don't do that. It's that simple. That's what I'm really trying to tell you. It is as simple as it looks. Go ahead.
So an inductor before when t is less than 0 is a short. What is it?
Here's the reason why, though. Understand the physics. When you look at an inductor in general, and you have a current I of t through it, and a voltage V of t, well, the voltage V of t is equal to L di dt. All right, this is the physics of it. If nothing changes with time, the voltage is 0. If that's a straight wire and the voltage is 0, it's a short. That's the reason. So at t less than 0, you all agree nothing changes with time, right? And when t goes to infinity, everything settles. It's at a constant state. Nothing's changing with time. The voltage is 0. It's a short, regardless of the current flowing. Y'all follow me on that, class? So now, getting back to this thing. You are right. There's nothing to sustain that current, so it's 0. Got me on that? Now, the next thing I've got is R Thevenin. How many can see what R Thevenin is without me redrawing? Can you all see it back there? All right, what is it? Man, there's only one resistor. Chances are it's that guy, sure. R Thevenin's 2 ohms. And what else? Tau is equal to L over R, right? So it's L over R Thevenin, actually. And I like saying this. Time constants have to do with one thing. The bigger they are, the slower things change, or the slower the rate of change. So a time constant is in seconds. Now just listen to me. The bigger the value of capacitance, the slower things change. The bigger the value of inductance, the slower things change. That means it's proportional to the inductance. With inductors, just because of the physics of the situation, the way they discharge, they are divided by R. With capacitors, they're multiplied by R. And it has to do with the differential equations that govern. All right? Now, sometimes people mess this up. Just make sure you do enough problems so you don't mess it up. Anyway, for ours, L was what for this problem? Now you got me one. It was 1?
1 Henry. It's right there on your, you saw it ready.
Yeah, 1 Henry divided by R Thevenin 2 is 1/2. All right, now we're ready to write that equation. We can say IL of t is equal to, what is K2 again?
0.
It's 0 because there's no current at t equal infinity. So K1 just becomes
3 over 2.
the current at t equals 0, right? So it's 3/2. And e to the minus t over, so it's really e to the minus 2t, and this would be amps. We're still not done. The question asks for V out of T, here to here. So what is V out of T? Just look. Go ahead.
IL times 2 ohms.
Yeah, it's just
I
R
R T.
times I times R, it's just 2 times that, right? Or it'd be 3 volts, isn't it? I mean, it's actually what? It's 3 e to the minus 2t volts. Agreed, everyone? Right? And honestly, that's how these problems work. Now, the main thing that people mess up, in my opinion, is this time constant. Because now you got a second type. It's not just R times C, it's L over R. And they will mess up oftentimes, not all the time. Oftentimes, they will not write an equation for the current. They will write an equation for that voltage. They somehow just disassociate with what I've been saying in class over and over again. And I don't know why, but on the internet, I know there's a lot of people that say, well, we write differential equations for this. You can. That's not the best way to do it. You can follow your Chegg people or whatever you want, and you will find yourself falling on your face over and over again in this class, because it's wrong. A lot of stuff they tell you will get you in trouble. Don't write diffy Q's or worry about that voltage or some other current. Only thing you care about is the current through the inductor. You listen to me, you'll be fine. Promise you. Okay? Now, any other questions? I'm going to go one more if I can. Good? Any? No? I'm always looking for things from the audience.
Can you do 3.39?
Yeah, I'll be happy to. I like that one. That's a good call. All right. Again, they're asking for something that is not the primary thing you're worried about, right? They're asking for that voltage. This happens in all the problems, just about. The question is not focused on the fundamental thing you worry about. So, if you don't mind, I'm going to go ahead and put in the direction of current this way. Okay? That's what we're worried about. We know the formula for that will be IL of T will be K1 e to the minus T over tau plus K2. We know that form, right? Now we go about our business. Just think about it right now. Force yourself to think. How would I go about doing this if asked to do it? Well, I always say find IL in the inductor for T less than 0, before the switch changes state, right? Can you all hear me okay? Everybody see this? So what does it look like? Well, before the switch is originally closed and it opens at T equals 0, right? So that's a short circuit. It looks like this. I have 12 volts, right? Then I have 2 ohms, And then I have another 2 ohms here, and I have 4 volts. Then I have the inductor. I'm going to draw the inductor like this because it's a short. And I want that current for t less than 0, right here. And then I have 2 ohms over here. Come on. Now you look at that, just take a second. I'm after that current. You probably can think of 3 or 4 ways to do it. You could do it with Thevenin's, make the low 2 ohms on the far right, correct class? Y'all see that? Sure, if I made this Thevenin, right, I'd find the open circuit voltage, then a Thevenin equivalent resistance, and then I could build a Thevenin equivalent circuit. That's one way. How many see that? Right? You don't see it. How many do see Thevenin right there? I'm trying to make sure I can read you good. You don't see it at all, or do you? You do? Okay, I gotta make sure, because I've gotta be clear about this. You could do it with loop analysis, here and here. You could do it with nodal, right? You could do it with source transforms. The preferable way that I would do it is source transforms, because it's the easiest. And of course, I look for the easiest way to get the answer I need. And I hope you do too. So you can see that I have these 2, voltage in series with resistances, right? Both tied to the same 2 points. Y'all see I could replace that with a current source that would be 6 amps in parallel with 2 ohms. Do y'all see that? I'm going to put it over here. So I can put 6 amps in parallel with 2 ohms. Y'all see that? Then what about these 2? Class?
2 amps.
2 amps in parallel with 2 ohms. How many see that? Please let me know. So this would be 2 amps in parallel with 2 ohms. We're right here. I haven't even connected that second one. And the last thing I'm going to do is connect the load. Because I want the current through here, so that's the equivalent load, isn't it, class? All right, so now what do I do with this thing? I've got the 2 in parallel with 2 is 1, right? Y'all see that? They're in parallel, aren't they? How many, y'all see that, class? Sure. So it's 1 ohm. What about the 2 and 6? And 8. Right, right. Now at that point, you can attach this resistor and just do current division. Y'all follow me? Yes?
In the problem, the 4 volts is written minus 2 plus.
Oh, it's the other way?
Yes.
Okay, I'm sorry. Then if
It's
it's
okay.
the other way,
You just subtract them, right?
right, then this is going to be 1. 4, right? Is
Yes.
6, so it'd be 4 going up. It would still be 1 ohm. All right? Thank you very much. So now over here what happens, I can put the 2 ohms, right? And that's the current I wanted, right, class? What's that going to be? We'll take the source current 4, right? That's the current in parallel with both, going through both. And then take the opposite resistance 1 over the sum of the 2, or 3. So it's 4/3 of an amp. Y'all follow me? Can I get a show of hands? I got a class waiting to get in. Y'all with me on this? Now just listen. Now, when the switch does its thing, just bear with me. What happens to this source, guys? Just answer me. Huh? This becomes non-existent, right? There's no way current can flow from that. Y'all follow me? A circuit, if it's only connected at one point to another thing, is no circuit at all. It has no effect. Y'all understand that? So it's gone. So what's the current as t go to infinity? Take one look. Give me a second. 12 divided by 4 is 3 amps. How many see it's 3 amps? How many see R Thevenin will be 4 ohms? Right? All right, you do the rest of this problem. But this is the kind of, I mean, if you're thinking clearly like that, you're going to do fine. Okay. We got another class. I'm sorry. I'm short. Thank you very much.